Good morning, everyone. I'm Zhang from Oil Crops Research Institute of the CAS. First, I'd say thanks for the kind invitation. Today, I will talk about developments and applications of micro, nano materials in mycotoxin detection, molecular warning, and control. Totally, there will be 5 sections. First, I will say something about mycotoxin and aflatoxin. As we know, mycotoxins are toxic substances produced by filamentous fungi, and many of them are second metabolites. Mycotoxins are very close to our life. They may in agro products, daily foods, and drinks. Maybe I can say something we like to eat, they like. Mycotoxins always threatening our health. Every year, they caused a great number of food loss and economic loss. Among mycotoxins, aflatoxin is a group with top toxicity and harm. In 1960, the famous Turkey event occurred in England. It caused over 100,000 of turkey died. During that time, no one knew the reason, so named it as X disease. Anyway, the event impacted on that Christmas Eve. Finally, the reason was discovered as aflatoxin, produced by Aspergillus flavus. After that, aflatoxin also caused a lot of human events. Now, we know that aflatoxin B1's toxicity is 10 times of potassium cyanide, and as type 1 carcinogen, contribution to liver cancer is up to 28%. And its contamination covers almost the whole food chain. Aflatoxin distributed almost all over the world and was found in over 100 edible products. We can find aflatoxin. So, how to find the toxin and the contamination risk on time, and how to prevent them, how to reduce them from the contaminated products. It's very important to ensure food safety. In order to find the toxin on time, we developed new materials to increase assay sensitivity. As we know, antibody quality determines immunoassay sensitivity and specificity. Mycotoxin belongs to small molecules. It cannot induce antibody. So mycotoxin has to be conjugated to some protein, forming immunogen. However, what immunogen structure can induce beta antibody? During the past, immunochemists have got a lot of knowledge about immunogen design. We mainly discovered the linking site rule and find the effect of food structure on antibody specificity. Linking site offsite moiety contributes on affinity, especially those immune active groups. Using the linking site rule, we developed a series of ultra-sensitive monoclonal antibodies for mycotoxins, includes aflatoxin, ochratoxin, their nano, and so on. Some can recognize a group of microtoxins, and some is very specific to only one toxin. Comparison to those published antibodies. Even so far, monoclonal antibody 1C11 is still the most sensitivity antibody towards aflatoxin. And 3G1 is the most specific antibody to aflatoxin B1, and 2C9 is the most specific antibody to aflatoxin M1. In order to increase antibody stability, we developed phage display technology for nanobody. That's VHH antibody. The size is from 2 to 8 nanos. We developed aflatoxin nanobodies. Our result found that the nanobodies can tolerate 70% methanol and 60 centigrade temperature. These materials were used for advanced immunoconins and low assays. For example, using aflatoxin and aspergillus flavor as an example. With the nanobodies, we developed the first method for simultaneous detection toxin and its microbe. In this case, the sensitivity of aflatoxin is 0.02 ppb and aspergillus flavors is 800 spots per gram mass. Using the above antibodies, we developed a series of immunoprobes, ImmunoGuard, Immuno-European, Immunoquarandots, and so on. Based on the immunoprobes, a lot of more sensitive immunoassays were developed, and I will show some of them. The first is ImmunoGuard method. 10 years ago, we developed the methods for single mycotoxin, and they have become classic methods in the market now. After that, we developed ultra-sensitive multi-assay methods for mycotoxins. These methods can detect several mycotoxins simultaneously. In order to give a detailed result, we also developed the digital immunochromatographic strip reader for Guard method. The reader can output the result directly. The second is Immuno-European method. In order to increase assay sensitivity, we enclosed a large number of European compounds in one bead, forming microparticle. You can see under the UV, the test line can see we learned the method is time result fluorescence immunochromatographic assay, shortly TRAPICA. Okay, it's an example. In this case, we used two anti-idiotype nanobody. We developed an ultra-sensitive TRAPICA for aflatoxin and their nano. Especially, the method can avoid highly toxic conjugates. And then we developed a smart portable TRAPICA reader with high sensitivity. Now the portable test becomes smaller and smaller, smarter and smart. Now we can use cell phone to read the result. Generally, TRAPICA sensitivity were over 10 times higher than ImmunoGuard method. The third is immunosilicon method. Using nanobody, we developed better environment tolerance immunoaffinity columns. It provided component for online analysis. It includes single target immunoaffinity columns and multi-target immunoaffinity columns for simultaneous analysis. Currently, our immunoaffinity columns can bind over 10 mycotoxins. And coupling our immunoaffinity column with UPLC mass, we developed an automated exclusion SPE UPLC mass system, and this can automatically carry out capturing targets, washing, and elution, and finally established an ultra-sensitive online analysis method. Okay, the above methods are for mycotoxin test. We can think if mycotoxin is detected, it means contamination occurring. So before the contamination, how can we find the risk? And is there a biomarker for toxin early warning? For this work, we isolated over 3,000 of aflatoxin producing fungus strains, and the samples were collected from 17 provinces of China. We investigated their producing aflatoxin capacity and their genomes. The results indicate that there must be some biomarker for toxin early warning. And then, how to find such biomarker? We designed a low nanobody own strategy, especially at least 3 strains with low, middle, and high producing aflatoxin capacity were used to select the nanobody. If the signal like the left picture, we can get it. With 6 years efforts, we really got a nanobody against the biomarker. And using the biomarker, we developed a rapid ELISA method for finding the fungi with high producing aflatoxin capacity in apple products. The method showed high specificity to those high producing aflatoxin capacity strains. And then we found that the biomarker PL8 peptide is produced before aflatoxin. So we can use it to find the contamination risk in advance. For example, we look at the second peanut. It looks like good and low aflatoxin, but using the biomarker, we can find the contamination risk before aflatoxin occurrence. Finally, based on big data, we developed the early warning method. We set up 3 levels. Low risk means products can be unworriedly stored or used. High risk means the products needs to be treated. And the middle risk means products need to be monitored. We also established a linear relationship between the biomarker and the producing aflatoxin fungi concentration in soil. And we can monitor the biomarker to give when and whether we need to prevention and control measures. With the early warning method, when we find a risk, we still need a green prevention method. Firstly, we developed microbial agents for aflatoxin control in field. And we have obtained 2 registration certificates of the Ministry of Agriculture and Rural Affairs. The agent has been used widely in China to prevent peanut aflatoxin contamination. Our results showed that aflatoxin in peanuts was averagely decreased over 60%, and even production was averagely increased 5%. Second, biomimic materials control. From series of citral derivatives, we obtained some very good fumigant candidates, and then we developed the fumigant prevention method. The duration can last 24 days, and the control efficiency reached over 93%, especially it's a safe green way. Thirdly, we developed a magnetic photocatalytic disinfection method. we found the active oxygen attack Aspergillus flavus and the destruction of fungal cell structure. Comparing to the control, aflatoxin contamination level decreased 94%. It shows a very good control efficiency. So if there is still some contaminated products by mycotoxin, how can we do? So we also developed the materials for green reduction of mycotoxin. First, we found that nano-sized carbon nitrogen seeds could degrade aflatoxin. However, the problem is the degradation rate was too low, only 31%. So how to increase the degradation rate? In order to get the answer, we investigate the degradation mechanism and the factors related to degradation rate. We found faster charge separation efficiency and a beta photocurrent can lead to higher catalytic performance. And that the active oxygens are the main radicals for degradation. Firstly, attack the carbon 9 site of aflatoxin molecule. According to the above finding, we fabricated these composites and then developed a lower and efficient composite photocatalysts. Using the above efficient composite photocatalysts, finally, we developed green photocatalytic technology for reducing aflatoxin, and the degradation rate increased to 95%. It shows environment-friendly, high safety, high efficiency, and reusability. On the other hand, we further found this bacteria can degrade not only aflatoxin B1, but also B2, G1, G2, M1, and even stereomethane with high efficiency. The capacity is many higher than the reported microbe strains. Using the strain, we developed the aflatoxin degradation method for peanut meals. In solid state fermentation, aflatoxin were reduced from 100 something to 30. And safety evaluation report for this strain and also the degradation products were obtained by a certifying authority. Okay, now make a technology conclusion. We focused on the vital industry problem, mycotoxin contamination, especially using aflatoxin as an example. We developed ultra-sensitive molecular antibodies, nanobodies, and immunoprobes for detection. Developed a biomarker for early warning, and developed microbial agents, biomimic agents, and photocatalysts for prevention or reduction of mycotoxin. All of these from aflatoxin system from field to farm. Based on the above technologies, we developed 13 standard methods issued by Ministry of Agriculture China, and since 2017, peanut aflatoxin control technology from farm to table was listed as main promotion technology by Ministry of Agriculture PRC. Chain and applications covered main producing regions in China. Also, our lab was selected as international mycotoxin test technology training base by EU Horizon 2020 and International Society of Mycotoxins. More than 150 trainees from 20 countries have been trained in Italy, China, and Thailand. The applications has achieved great social and economic benefits, and we obtained several government awards, includes China National Technology Invention Award, ranked second. It's very difficult to obtain. So I want to say thanks for the support from Ministry of Agriculture and Rural Affairs, China, Ministry of Science and Technology, China, Natural Science Foundation of China. Say thanks to my colleagues, master and PhD degree students. Also say thanks to my international and domestic friends. That's all. Thank you very much for your attention.